Hello everyone, welcome back to my channel Physics with Sebi. Today I came with an interesting problem. First I will read this problem without delay. A light rectangular container of length L and height h is filled to the brim with water. The container is placed horizontally on a rough cylindrical log of radius r as shown in the figure. At what r container will be in stable equilibrium. Neglect surface tension. My little cutest friend Mr. Tom requests you that get a try to solve this problem by using the pause button. Now come to the solution. It is given in the problem that this is a container filled with water up to its brim whose length is L and height is h. And this yellow line is line of symmetry passing through its center of mass, and P is the contact point of this container with the log of radius r. This log is cylindrical shape. Here the question is, does the container comes back if tilted slightly? For this, you tilt this container through an angle alpha which is very small. Then the contact point shifted from P to Q towards right. Therefore, the center of mass of the water also shifts towards right. At the point of contact Q, draw one vertical line. Then, the displacement of the contact point is greater than the displacement of the center of mass of water. Then, the moment of center of gravity about this point of contact rotates this container in counterclockwise direction and bring back this container to its equilibrium state. Right? The displacement of contact point PQ is equal to R alpha. Okay, it is done. But the displacement of center of mass we have to calculate in two steps. One is due to tilting and second one is due to spilling of water during the tilt. Therefore, the total displacement of the container x is equal to the displacement due to the tilt x naught plus the displacement of the water due to the spilling mass delta x. Here we can write the displacement due to the tilt x naught very easily. Here you see the height of the container is h, the center of mass is at h by 2 distance from the bottom line. Here this yellow line is symmetrical line of the container when it is in equilibrium state, and this is the symmetrical line in tilted position of container. These two lines meet at one point just below this bottom line. Therefore, here to here also we can consider as h by 2 distance. Therefore, due to the tilt, the displacement of center of mass we can write as x naught is equal to h by 2 alpha. Here the angle is alpha. Here this is the approximation. The exact value we can write as h by 2 sin alpha. Here alpha is very small, therefore which is equal to h by 2 tan alpha, and it can be written as h by 2 alpha. Therefore, the displacement of the container due to the tilt I can write h by 2 alpha. In step 2 we have to calculate the displacement of the remaining mass. How to calculate it? During the tilt, some of the water is spilled out of this container. The removed mass forms a triangle here, that is ABD, whose center of mass is at O2. The removed mass I can write as M1 and it is supposed to be concentrated at point O2. From this base of the triangle, the O2 distance is L by 3. But from this line is line of symmetry in the tilted position. From this line, the O2 distance is minus L by 6. Why I am writing minus L by 6 means I take this line of symmetry as a reference line. Isn't it? Therefore, by using the concept of negative mass, I can write the displacement of center of mass of the remaining mass can be written as m its position is 0 minus removed mass, its position is at x1 by m minus m1. This total mass is supposed to be on this reference line. On this reference line, its horizontal coordinate is 0. From this reference line, the removed mass is at a distance x1. Therefore, I can write as minus m1 x1. This is formula in negative mass concept. Therefore, I can write like this: delta x is equal to minus m1 x1 by m minus m1. Isn't it? For small alpha, the removed mass is very small compared to total mass. Therefore, m minus m1 can be written as m only. Delta x is equal to minus m1 x1 by m. The m1 by m2 ratio we require. How to calculate m1 by m? m1 is the removed mass, m is the total mass. Isn't it? For this, here you see, this is the area of the triangle due to the removed mass. That area can be written as S1 is equal to half L square alpha. The area of this container, the total area of this container is S is equal to LH. The ratio of M1 by M is equal to half L square alpha rho B by LH rho B. Volume into density I write as. From here I can get L alpha by 2H. We will get delta x like this: L square alpha by 12H. Now the total displacement is equal to the displacement due to the tilt plus the displacement due to the removed mass. Due to the tilt h by 2 alpha plus due to the removed mass, this value, that is L square alpha by 12H. You have to substitute. What is the condition of stable equilibrium? The displacement of contact point should be greater than the displacement of center of mass of water. That I write here. The displacement of contact point is R alpha greater than the displacement of center of mass. It is written in two steps. One is due to the tilt, other one is due to the removed mass. Alpha is greater than 0, therefore R should be greater than h by 2 plus L square by 12H. This is the solution of the problem. If you like this problem, please like, subscribe, press bell icon and share the channel to get more new problems. Next time I will back with another brilliant problem.